This video is on gas law relationships. So just quickly, what are gases? So we don't forget. All right, so gases, right, are a phase. So things can be solids, liquids, or gases. For gases, that's when your atoms or molecules are very spread out. Because they have a lot of energy, so as they're spread out, they are constantly moving very randomly. So they're very spread out in constant random motion. And as they're moving around, they are colliding with themselves and their container. Random motion colliding with container and each other. And what you have here then is, because they're going to spread out and take whatever volume the container is. If there's no container, they're going to just continue spreading and moving around. But you're going to have actually more empty space when you have a gas in a container than you are actual matter. Like your atoms and molecules are so small compared to the space between them that they're, essentially zero. So more empty space than matter. All right. So, what kinds of things do we measure with gases? Well, things we measure are the two we've already talked about, which are pressure. We use P for pressure. And T for temperature. And with these, just a quick reminder, pressure is the force, right, divided by the area. So it's how much push or pull over a certain area. The temperature, right, is just how hot or cold something is. Okay, it's related to the kinetic energy of the molecules. And then the other two are things you're familiar with, which are volume. So a capital V for volume. And volume is how much space something takes up. And then the last one is moles, right? And that's just how much stuff you have. So that's your amount. And the letter we use for moles is a lowercase n. We can't use m because lowercase m is mass. So, which mass and moles are related, but we use n for moles. Okay, and because I'm going to use these letters when we get to our next part. So there are four what we call individual gas laws that show relationships between two variables at a time. So you're going to need to know which variables go with which gas law. The other ones are constant of the four. So two are going to be variables, right? Meaning change. Variable means change. And two of them are going to be constant. The other two will stay the same. And then by relationship, I mean, will it be direct or inverse? So quick note over here, a direct relationship is when the things go in the same direction. They change in the same direction. So they're either going to both, and I'm just going to do arrows to show this, to indicate this, either both increase, or as one increases the other, as one decreases, the other also decreases. Inverse is opposite. So that would be as one changes by an increase, the other would change by decreasing. All right, so Boyle's law is our first one. Boyle's law is when pressure and volume change. So that means moles and temperature are constant. So moles and temperature aren't changing, but if I change the pressure, the volume will change. Or if I change the volume, the pressure will change. And the relationship between these two is inverse. So as the pressure goes up, the volume will go down. Okay, so think about why this would happen. As you go from, let's see, we'll do a little diagram down here. Or actually maybe right here. If this is my volume, versus this as my volume. Okay, think about the molecules inside of here, right? We've got the same number. There's my moles, same amount. The temperature is not changing, so they're moving at the same speed, right? Same energy. But think about the difference between these two in terms of volume. Obviously, and I'll label them 1 and 2. Obviously, 2 is bigger. 2 has more volume. So the volume gets bigger as you go from 1 to 2. What happens to the pressure? Think about how they're colliding and how they're hitting that force over that area. As they're more spread out over here, there's going to be less pressure. They're hitting less. Over here, tighter space. They're going to hit each other on the sides of the container more. So this is more pressure. So as you go from 1 to 2, your volume gets bigger, your volume increases, and the pressure decreases. That is Boyle's law, relationship between pressure and volume. Charles' law is a relationship between volume and temperature. And so that means your pressure and your moles are constant. So we're not changing the pressure. We're not changing the moles. This is a direct relationship. So if you have a container with flexible sides, let's say, right? So your volume can change and you increase the temperature, those molecules are going to move faster, hit the sides more. If the sides are flexible, it's going to spread out and get bigger. Okay, so direct, as the temperature increases, the volume, they get bigger, would also increase. Gay-Lussac's law is a relationship between pressure and temperature. So this is where your volume and moles are constant. This is also direct. Okay, so if your volume can't change, you have a rigid container and you increase the temperature, right? Those molecules are going to move faster, but they can't change the shape of the container. So that means they're going to collide more and harder, so your pressure would increase. Increase temperature, increase pressure. The last one is Avogadro's law, which is volume and moles, right? Avogadro, it has to do with moles. Remember, that's Avogadro's numbers, how many atoms or particles are in a mole. So our pressure and temperature are constant. This is also direct. If I add more mass or matter, right, I increase my moles, my volume, it's right. If the sides are flexible, it's going to get bigger. If I add more stuff, my container needs to be bigger. Okay. So couple other examples besides what I've just talked about. And maybe you've experienced some of these. So let's say you're inside and you go and you buy, or you have in your house, a helium balloon. So inside that balloon, right? Okay, so helium balloon, right? Oops, it's fully inflated, right? Perfect, great, okay. And then you're gonna go take this balloon to celebrate someone's birthday, and it's the middle of winter here in Minnesota. And so outside, if it's cold out, right, in the middle of winter, that balloon is gonna shrink. Okay, and why is it gonna shrink? Because you're going from a temperature of warm to cold. So your temperature is decreasing. Now look at the volume of those balloons. This volume is clearly smaller. Your volume also decreased. If you go back up here, volume and temperature. This is Charles' law. This makes sense. That's direct. As the temperature goes down, right, the molecules in here slow down and they don't push on the sides as much. So it decreases in volume. So this is Charles' law. Oops. And this is direct. Okay. Another one, let's say it's cold out. Okay. And your car tire needs air pressure. So you go outside, here's my awesome picture of a car. I'm just going to do the front. Okay. And you inflate your tire to the pressure amount that it says on the tire. Okay. Say label. So on your tire, you'll notice it tells you what to fill it to, what pressure. Great. You fill it up to what it's supposed to. It's max. You're like, awesome. You drive off. Then it warms up. All right. So when it warms up, our temperature is going to increase. Now let's make a little prediction. We're talking about pressure here. So our pressure, if the temperature goes up, temperature and pressure are related directly. So if the temperature goes up, I hope you're already thinking the pressure will also go up. So think about that tire. Okay, so here's my tire with my pressure. Okay, and look at that beautiful drawing. And it's actually going to increase in pressure. And when that happens, your molecules are pushing way more and harder. And what can your tire do at this point? Well, sad to say, it could blow. Okay, you could pop your tire. Could pop tire, right? Because the pressure also increases. So you have to be very careful when it's cold out not to inflate it all the way, because as it warms up, it will inflate more. Okay, so this is Gay-Lussac's law. So this is also direct. Those are some examples of these 4 individual gas laws.